Today we'll talk about a particular collection of charges called the electric dipole, which is not fundamental but comes up a lot, so it's worth talking about. Two equal but opposite charges separated by a small distance, and we want to emphasize that a small distance, is known as a dipole. An electric dipole in this case, because they're electric charges. Eventually we'll have magnetic dipoles, etc. This figure shows two examples. There's the Mickey Mouse molecule, that is water, which is a dipole because the hydrogens have given up some fraction of their electron, and so they're a positive thing, and the oxygen has accepted that, so it has some excess negative charge, and they're spatially distinct, so there's some small distance between them. This is what's called an induced dipole. The electric field moves negative charges towards the back of this and leaves, therefore, some positive charges up here. Again, we're talking about tiny shifts. We're not talking about like massive movements, but enough to create the effect of a negative here and a positive here, separated by some small gap. We end up defining something called the dipole moment, which we represent quite badly with P. This is not momentum. It is an unfortunate choice. There are many unfortunate choices in physics notation. This is one of them. We describe the dipole as having charge Q, where we take the positive charge. A dipole always has equal and opposite charges, so it makes it a dipole. So we reference the positive charge concretely, not the total charge on the dipole, which would be 0. And then the dipole separation, S. Be aware that a lot of textbooks will use D instead or X, and so there's no standardization here. This textbook chose S, and so we define the dipole moment as being QS, and it points from the negative to the positive charge. Probably not really worth emphasizing too much, but they do here. Since we have Q times S, we have C times M, or coulombs times meters as the unit. Even though the dipole has no net charge, it definitely has a field. We can look at two important cases. If we're on the axis of the dipole, for instance here, then we know the positive charge is going to repel at positive charge over there, so the electric field points away. But the negative charge is going to pull a positive charge in, so it points in. But the actual electric field is just the sum of those, which in this case points upward a little bit. And we can see that why does it point upward? Because the positive charge has to be has a stronger field than the electric charge because it's closer. And that's the key thing, all right, that this distance is less than that distance. And we know there's a 1 over r squared dependence, so it's pretty sensitive to distance. If we're on the perpendicular bisector is the other interesting place. And here we see that the positive charge would tend to create a field pointing this way, but the negative charge would make a field pointing this way, and their sum is downward. All right, so somewhere along the line, the field has changed sense. It can be shown that the electric field at a point on the axis of the dipole, on the axis, let's stress that as is approximately 1 over 4 pi epsilon naught, that constant we've been carrying around, twice the dipole moment over the distance cubed. Notice that ends up being the correct units because the dipole moment has a meters in it. The r cubed has a meter cubed in it, so we get charge over meter squared. Correct units, yay. But the idea is that we usually don't have options on this. The dipole just exists, and we depend on how far we are as a cube, all right, what we may call inverse cube law. Dipoles fall off much more quickly than point charges. Why? Because they look almost neutral, right? As we get further and further away, they look more and more neutral because the dipole separation becomes very small compared to the point separation. So they look almost having 0 charge. Along the perpendicular bisector, we get the same sort of thing, but notice that we still get a cubic dependence, but we've got an extra factor of 2 here that has disappeared. All right, there was a factor of 2 on the axis, and there's not the factor 2 on the bisection. You can think of it as a mnemonic, not really, but bisection means divide the axis field by 2. If we actually sketch out the field, then we get in vector notation, we get these vectors. If we do the Faraday field law, we get this kind of interesting thing where the fields, of course, point away from the positives and towards the negatives, as they must. But we get this kind of weird bending here. And we'll see that bending a lot later on, something called fringing fields, and they can be important. Right now, it's mostly, again, notice how complicated the field is, except in the two very simple cases we did. On the axis is very simple, and all on the perpendicular bisector is very simple. Everywhere else, it's a bit of a mess. All right, an electron is a plane that bisects a dipole. What is the direction of the electric force on the electron? So we have to be careful here because we want the force. So the field, we'll put the field in blue. The field of the dipole is always opposite to the dipole moment, at least on the perpendicular bisector. So the field is looking like this. The strength there is all entirely wrong. It should definitely be weaker. We can sketch that a little bit better and say that it gets weaker as you go out. Something like that. But remember that the force is Q times the field, and here RQ is negative, right? Because it equals minus the electric charge. So the field force is opposite to the field. It points upward. So we get answer A. Consider a dipole in a uniform electric field as shown. Which statement would best describe its immediate subsequent motion, assuming it was released from rest? So choices are, does it move left, move right, or not move at all? And second, does it rotate clockwise, rotate counterclockwise, or not rotate at all? Here we'll probably want to find the forces. So the force on the plus Q charge in a field pointing to the right is going to also go towards the right because the field tells us what direction a positive charge feels a force. But the negative charge feels an opposite force. We can see that those two forces cancel. So the center of mass will not rotate, will not move. The center of mass will stay right here. On the other hand, the sum of the torques is not zero because the positive charge tends to torque it clockwise, and the negative charge tends to torque it clockwise. So it will be no motion of the center of mass, but clockwise rotation. And this is not really a dipole, but it's sort of the natural complement of it. What if we had had two positive charges rather than a positive and negative charge? Of course, this would not be net neutral. It would have a charge of +2 on it. And we do see kind of this weird thing where far away, right, near this thing, it looks sort of, near the upper guy, it looks like a point. So we see them radiating out like we expect. But in the middle, they tend to cancel out because the charge here is repelled from the top guy a lot, and then but repelled by the bottom guy a little bit, and that tends to make them smaller. Now, they're not really zero except here. We've just got no field here because compared to these points, it's so weak that we can't even draw one without putting the density too high. Is this important? No, although it's kind of useful because it's a Faraday approach where we can see, if we think of these as like those little troll dolls with the crazy hair sticking out, as we try and push the positive charges together, the hairs kind of bend against and put pressure on each other, which is why they're repelling. Is it really why they're repelling? I don't know, but from the Faraday field view, there's a way of saying it's the presence of these lines that are causing this pressure, which is how he viewed it.